Hello, everyone. This time I first unmute myself and then start speaking. So this is a small step for everyone, but big for myself and my intelligence, artificial intelligence. Joking, of course. Okay. Thank you all for staying with us. The next talk will be very, very, very interesting, to be honest, and it's going to be delivered by the Mate Picukaric, and he's machine learning researcher from the artificial intelligence researcher from Atomic Intelligence, which is also one of our closest partners in Croatia. What will the talk be about? It's audio separation using neural networks. And basically, as an introduction, I would like to say the common process in music production is combining tracks of individual instrument sources into a mix. And basically, what does it mean? You have 4 or 5 different instruments, and you put it inside of one whole. Basically, the question that audio separates using neural network possesses: can the individual tracks be extracted from the mix using deep convolutional neural networks? The talk will try to answer this question, focusing around the approach to solving this issue and the problems that arise in the processes. Without further ado, I would like to call Mate to join us and to start with this exciting talk. So, hello, Mate.
Hello, Alex. Thank you for the introduction. So my name is Mate. I'm coming to you from the beautiful city of Zagreb, and I'll be talking about audio separation using neural networks. I come from the company Atomic Intelligence, which is a data warehouse and business intelligence company that does big data technologies, AI research and development, and much more, especially funding these kinds of interesting projects that I'm currently working on. The introduction should be more focused around what audio is. So what we are trying to do is decompose the audio track into elementary sources. As Alex has already said, it's a common thing to have a song on the radio played, which combines the contributions of different instruments into one track, and that's something that is very, very common. The question that we try to pose is, can the inverse be done? So, can we use convolutional neural networks to extract the contributions of these different instruments? And today we are trying to, considering that a lot of people aren't working with audio, we're trying to give you a closer look about what does it look like to use audio and to work with audio in these kinds of situations. We are currently working at this project because it's interesting. As you can see behind me, I'm a musician. I've been one my whole life, and I'm very, very grateful that I can be working on this project with my colleague Tin Hadživeljković, who's also a musician. So we're very, very passionate about it and very excited that we can share what we managed to do with you over here today. To recap audio in a couple of sentences, audio is produced by vibrations of a material, and it's essentially longitudinal vibrations of air, which is received by the left and the right eardrum, which are positioned, of course, in our ears. To give a comparison between the ears and the eyes, there's 1 eardrum per ear receiving the vibrations, whereas there are 6 million cones and 120 million rods, which is around 130 million photoreceptors per eye, which is a lot more info that goes into our eyes. So it's very surprising that we are able to distinguish between different contributions in our ears. So, for instance, if 2 people are talking, you can clearly distinguish which one of them is talking and which one of them is talking what. But the interesting thing is that we are able to do that with only 1 receptor, actually 2 receptors, but you get the point. The recording of audio is usually made by transferring mechanical vibrations to an analog signal, which is a vinyl or a cassette. And the similar is done with a microphone, except in modern days, it's later converted to digital. So CDs and streaming services all save a digital copy of the audio instead of an analog one, which is the case with vinyl and cassette. The thing that is very important in audio analysis is frequency analysis. The importance of frequency components is something that is very clear in a lot of scenarios, and it's something that is often used but maybe not recognized when we listen to a lot of things. So, for instance, when you want the bass to really hit you, you have the difference of bass and treble. That's something that is inherently frequency related. Or high and low sounds. Let's say women have a higher voice than men. This man has a deeper voice than this man. And especially melody. So melody is something that is very frequency related. And a simple representation of a frequency analysis is given here on the right with this animation that is of an equalizer. So This gives us a time-related frequency analysis of an input track where the columns more to the left represent the bass frequencies and the column more to the right represent the treble frequencies. And as we will see later, this is very, very similar and can serve as a great introduction to realize what kind of data we are giving the network. And one important thing, let's say the unit of our frequency analysis is always the sine wave. For those of you who are more based in digital signal processing will know that the Fourier transform relies heavily on sine waves. So if we say, let's say that a sine wave of a specific frequency is like the unit of frequency analysis, we expect the spectrum, which is the thing that we will discuss later, of a sine wave to be just this single column without anything over to the left or to the right. This is because the input audio, which would in this case be a sine wave, is composed only of one unit of audio. Of course, for a more intricate input audio, we would have a more intricate spectrum of frequencies. That is something that we will see later. Another important concept is the harmonic series. So this might be a little bit harder to tackle in such a short time, but the idea is this: if you have two musicians, if you have a musician in a room and you play, let's say, a C1 on a piano and a C1 on the guitar, they would all agree that it's the same tone. So the question is, how come is it the same tone when we obviously have a different different audio input? And the idea is that tones, which we can perceive as like musical and we can sing to, have this specific distribution of frequencies in the frequency spectrum, which are given over here. So these are the harmonics, and they always come in the same pattern. So when we have a piano and a guitar, they have these harmonics in different amounts, like in different contributions, but the fundamental pitch, the basis, is always the same. Imagine this: we're gonna have quite a lot of food analogies because it's very easy to discuss these topics this way. But imagine this if making a meal which has the same base component but different ingredients in different amounts. You always have the same base component, or you could always say that the risotto is based on rice, but you always have different varieties of risotto based on the ingredients that you put into it. So this is the same thing in frequency analysis. The thing that we will be using is a spectrogram. So a spectrogram is like a 2D array where the size of the number, where on the x-axis we have time, and on the y-axis we have frequency, and the color of the cell, in our case the largeness of the number, corresponds to the amount contributed by that frequency in this specific moment of time. Not to confuse you very much, but let's take this example. The first thing that we have over here, our spectrogram, which is something that I feel that we have all seen on radios and visualization when we input it. So we take this animation and let's split it into frames. So let's take the 3 frames from that animation and put them like this. Then we flip them around. Each of these animations represent one point in time. Then we flip them 90 degrees counterclockwise so that they look like this. This one corresponds to this one. This one corresponds to this one. This one corresponds to this one. And then if you could imagine, we could flip it around the y-axis. If we imagine this to be the y-axis, we flip it around the y-axis so that all of the columns point toward us. And so we get this stacked image. Imagine like 3 stacked books of these 3 images. And each column over here represents one image. So this column would represent this one, although very poorly drawn in MS Paint. This one would represent this one, and this one would represent this one, even though the colors don't really match. But that's just to give you a greater sense, because spectrograms can look very intricate. For instance, like this one over here. But not to get frightened, you've already seen this in certain sense. It's just that the time resolution and the frequency resolution is a bit greater. So the darker points represent more silent contributions of frequencies, whereas the lighter points represent more influential contributions. So over here we have a spectrogram of a mixture of a couple of instruments combined together to make a specific song, and it's very interesting that you can actually hear. That you could actually see the harmonic series over here. So if we take, instead of the mixture spectrogram, we have available the voice spectrogram. This looks something like this. we can actually see it being hidden inside the mixture. If you can see, these lines over here really match the voice spectrogram. This. So you have them over here and you have them over here. And what is interesting is the same as we had in the harmonic series, you can really see the fundamental and the harmonics coming into in a pattern. So you really see this pattern of harmonic instrument. And you have some contributions that are not very visible. For instance, this one is some other instrument that is also appearing in a harmonic series. So it's quite interesting to see, to be able to see these kinds of effects using only this spectrogram, which is not really the case with audio, with raw audio. The thing that makes audio versus images really stand out is the problem of superposition. So the same way as we talked about two people talking, there is only one eardrum that receives all of those signals. And if you were to look, you would have only one waveform, but you could really tell that there are two people talking in that waveform. So the problem is the two signals interact. And the separation problem is finding the contributions of different sources in the final sum. So when we get the final recording of two people talking, we want to know what the contributions are, and could we separate out just a track of one person talking and just a track of another person talking. So over here we have a simple visualization. Let's take a look at this oscillating function. And this oscillating function, let's say that this is an audio track, and when you would add them all together, so if you were to superimpose them, let's say that this is one speaker and this is another speaker, they would go silent. Okay, because the hill would cancel the valley, and the hill over here would cancel this valley, so you would get silence. Similarly, if two hills were to collide, were to match, you would get a hill that is twice as high, and the same goes for valleys, which would be twice as low. And if there were a little bit misaligned, you would get something that is in between, so a little bit smaller than this one, but definitely not quite. And the problem with superposition is this: there isn't just one way that we could get from here to here. This isn't the only combination of contributions that could give us silence. For instance, if we were to have these imaginary speakers talking in this kind of way to perfectly quiet each other out, to perfectly destructively superimpose, which is the physical term, this could also be done with just one person being silent. So there's actually an infinite number of ways from which we can go from here to here. And the problem with superposition is finding which of those contributions are. Considering this is an AI conference, it suffices to say that we need to show some AI in the presentation. The first thing to note is this segmentation problem. This is quite familiar, where every pixel on the image is labeled. Every pixel belongs to only one label. So if you see over here, we have this car that is in front of the building. And the thing to note is, for instance, this pixel, which is labeled red over here, belongs to the car, even though it covers the house. This is not something that we face in audio. So imagine we have these circles. Okay, let's imagine that circles A and circles B are opaque instead of transparent. Circle B covers circle A, and this is why in the intercept we see only B. So there is no mixing of the two of them, which is not the case in audio. The audio is more reminds us more of transparent circles of specific colors. For instance, let's say that this is a transparent green circle and this is a transparent red circle. Their intercept is obviously yellow. This is represented over here. But the important thing to note is that there is no way of telling in this naive sense, if we get a yellow pixel, is it a pixel that is red and green combined, or is it simply a yellow pixel from a yellow object? And that is the problem of superposition that we face in audio separation. Another problem is phase. So not to get very into it, if we actually do find the specific contributions of some frequencies that we saw in the spectrogram before, where we really do find the spectrogram that is the spectrogram of the voice that is hidden in the spectrogram of the mixer, we still haven't solved the problem yet. And to make a little bit more sense of it, imagine that you went to your local fine dining venue and you ordered a risotto, and it was the best risotto that you've ever had, and you really want to replicate it at home, and you really want to make it for your wife or your husband or your spouse or your dog if you feed your dog. So and let's say that there exists a machine that you can input food into, and that can tell you the specific amounts of the ingredients that were in that dish. So you would take the risotto, you would put it into this fantastic machine, and it would input this sort of recipe. Can you replicate the same risotto just from this recipe? Obviously you can, because you cannot, because you really need the specific moments at which the chef put these ingredients into the mixture. And the same goes for audio separation. If we do find the correct spectrogram, we need the phases that are needed to connect the time intervals together. This is something that is represented over here. So over here we have a sine and a cosine. One is drawn red and one is drawn green. A sine and the cosine have the same spectrum because they're the same unit of frequency, as we said, just a little bit delayed. So we can see that the green one is a little bit delayed from the red one. The problem arises is that when the superposition takes place. So over here, if we continue these lines a little bit more, we would get two same oscillating contributions. The problem is that the amount of delay that they have in between each other gives us a different result every time. So this is very, very important, and this is a problem that we approximately tackled in our solution because it was really, really required. The data set that we use is a MUSDB18 data set that we found. It's 100 songs recorded at 44,100 hertz. It's each song is composed out of 5 tracks. So there is one mixed track. Each one is stereo, even though we did our analysis in mono. Each song is composed of 5 tracks. So one is a mix, and you have 4 stems. So we use the mix as the input value, and we use the stems as target values. We use PyTorch to write our code, and the hardware was an NVIDIA RTX 3090 GPU. The interesting thing is that the biggest problem we faced during our training and the development of this program was finding the right cable for the NVIDIA RTX 3090. And I hope that somebody can relate in this conference, because we couldn't find the cable anywhere. We ordered, because we wanted to connect the NVIDIA to our server room, so we ordered 2 cables from AliExpress, and neither of them came. I think we waited for them for like 4 months, and then our colleague managed to get one from Germany, and now we finally have the cable. So we hope that the results for the next conference would be much, much better. The general training pipeline is this. So we first load the data with transformations, which I'll get into in a second, and do an audio random crop. So we don't input the whole song into the network. This is because the GPU fills up too fast, and we cannot proceed with the calculations. So we only take 4 seconds in length. We compute a spectrogram for each audio crop, convert the spectrogram to a PyTorch tensor, which is a size of 512 by 512. We chose an optimization algorithm of Atom, and we pass mini batches of size 4 or 8. This is also because we fill up the GPU too fast, so we had to scale down the mini batches, and the parameters obviously update through backpropagation, and we repeat the procedure for 150 epochs. The transformations that I would really want to get into are identity and kernel, we call them as such. So let's, for example, look at how you would train a baby to do the same procedure. This was an analogy that we hold very dearly. So a baby would probably have a problem with recognizing the specific instruments at first, because you're training it to do a very intricate task. You're training it to find the contribution of a specific instrument in a mixture, which is not very easy, knowing that you don't really know how the instruments sound like. So instead of giving it a mix and expecting, let's say that we train a network for drum separation. So instead of giving it a mix and expecting to get drums out, which we call normal mode, at the first couple of epochs, we decrease the ratio of the normal mode to identity and kernel throughout the training period. So we give it drums, and we expect it to output drums as well. So the target is the same as the input, which we call the identity mode. And then we give it another instrument, which it isn't being trained to separate, so a guitar, and expect it to give out to output silence. And this is called the kernel mode. So this actually does reduce some bleeding of instruments that are connected to the that clash in the frequency spectrum or in some character, which I will get into a second. So of course, considering we are at an AI conference, it suffices to say that we need to talk about the network that we use. The network we use is a UNet architecture. It has kind of an encoder-decoder structure if there are people that are not familiar with the UNet. So the size of the image reduces down to the bottleneck, down to the bottom of the net, and then it decreases again. So this is kind of an encoder-decoder structure. The difference that the UNet has compared to encoder-decoder is these skip connections. So you have these skip connections that are concatenated with the parallel layer in the up part. So this the output of, let's say, the first layer is saved and later applied over here, and then you do a double conv on both of those layers concatenated in the channel dimension. And this is done because you want to have this influx of raw information, of more raw information, and not get everything from the abstract part, from the abstraction that is done by the encoder. And so the results are, to me, they're very interesting, and I'm quite satisfied with what we've been able to accomplish so far. So we'll take a short listen of a couple of examples. This first one is Wind Up song by Julian Lage. And if this gets too loud, just yell or something. Probably somebody would tell me if this gets too loud. Oh, sorry. So what we managed to accomplish is this. So as you've heard, you probably heard some bleed from other instruments and some specific artifacts coming from the phase correspondence. So the clashing in phases, which isn't quite perfectly approximated. That's a common thing that we are trying currently to fix, and that we are trying to improve our model. But I feel that this is a great start, and this is a great result. The problems that we have are with overlapping instrument, and I see that somebody is asking how much interference and harmonics between different instruments, such as voice, guitar, are giving us headaches. One thing that we faced is instruments that are similar in the harmonic spectrum, and I feel that instruments that are similar in character also have the specific problem. It has a specific problems to separate. For instance, when you take a double bass, I don't know if anybody has heard a double bass live, but it has this this percussive element of the string bouncing back and hitting the fretboard, and this can very clearly be heard over here in this track. And so the problem is that our network misplaces it for drums, so we get this. I don't know if you can hear the percussive elements. I don't know why I was talking over this. Also, let me play it once more. Yeah, and another problem arises from instruments that are clashing in the frequency spectrum. So this is apart from the Dire Straits song "Sultans of Swing," where there's a guitar line right after the vocal line. So we get this.
You get a shiver in the dark. It's raining in the park. But meantime.
So the problematic part is this bend, like wow, wow. And we really managed to solve it using our identity not solve it, but suppress it using our identity and kernel transformation. So the vocal separation sounds like this.
In the park, meantime. Sound of the river, you stop and you hold.
This is without the identity and kernel transformations, and when we apply them, you really do hear suppression of the guitar.
It's raining in the park, meantime. Sound of the river, you stop and you.
Hopefully you could hear that it's much more quiet. And finally, what are our goals and progresses, and what are our problems? What we want to do is expand the other section, like because the files are separated in mixture, vocals, drums, bass, and other instruments. The idea is to be able to have a network that could separate out a lot of other instruments, and not just these ones that are available to us. The problem that we come to is finding the right data, because there aren't a lot of songs that are available that have stems available for them. So if you hear a song on the radio, there's a great chance that we won't be able to get the stems. We would have to talk to the publishing companies, and they would have to be really friendly, and we would have to, it would be really complicated, and it's complicated to get these kinds of data. So what we've envisioned for our next step is trying to paste instruments that don't even belong to the song. So let's say that we have dire straits over here, and that we find a fun video of somebody soloing on the saxophone, and we really want to train the network to separate out a saxophone. Then we would just, even though the video of the saxophone player isn't playing on the dire straits song, we would still paste it onto the video and ask the network to separate it. Truth be told, this is a little bit of an easier task, because there isn't a lot of overlap in time, which is the case when you have rhythm. So it won't overlap with the, let's say, the drums and the bass and the other instruments. And considering that they're not probably not playing in the same key, it would have it wouldn't have as much of overlap in the harmonic series, considering that it defines the timbre of the instruments, and it's related to the bass tone. Another thing that we're trying to do is automatic instrument recognition, so the network to be able to recognize which instruments are present in the track that we are playing. Currently, we are training a separate network for each instrument, but the goal later on is to have a network that could separate out all of the instruments at once. And this could give us an opportunity to create something called reconstruction loss, where we would also grade the workings of the network by how well it could replicate the input data by combining all of the output stems of the output tracks. So yeah, we would also like to tackle data synthesis, which is trying to synthesize tracks and stems using MIDI, which is a common file type used in audio production. And today, the virtual instruments available online that are either pre-recorded or synthesized are very, very good and very realistic. So we would like to try and make an automated software that could generate data for us and serve as a way for training the network. And at the end, we would like to try something with the hybrid waveform and spectrogram. So giving the raw data and the spectrogram at the same time, because this could potentially help us in tackling some problems with noise, and regarding some instruments being more noise oriented and some instruments being more tone oriented, to be able to get the best of both worlds, actually to get both worlds, and to be able to separate the contributions more clearly. And other AI projects at Atomic Intelligence, for instance, we are not only doing music. There is a project working on technical drawing analysis, where we are trying to analyze the technical drawing and to get the most important segments out of it, and entity recognition. So this is analyzing text and trying to find specific entities in the text, like the name and the last name of the person that wrote the document, and the name of the company, and so on and so forth, which is very easily recognized. So are there any questions?
Okay, basically we are run out of time, but I will like to take, because we have a 15 minutes break, so we can have one of the questions, and maybe we can do the other questions. You can record the answer and then send to us, and we'll post that. First question is maybe a bit broader, but I would like to ask you, how can you put this technology into the product? Can it help you to learn musical instruments? If yes, how? To play musical instruments.
Mm-hmm. The thing that we would like to maybe do in the future is something like a karaoke machine, like being able to take out the voice from a track and be able to make karaoke. But an interesting thing that is also faced is how well people are able to do this problem themselves. So being a musician, I have no problem with separating out the contributions in my head and figuring out what the contributions of a different instrument are in the track. But I know that people who are just starting out don't have the same sort of capability. So when, let's say, transcribing a solo, trying to figure out what a person was playing in some song, it could help being able to separate out only the contributions and to learn it. And that way, it could help with gradually improving the knowledge, gradually improving the ability to transcribe.
So basically, right now, Mate, I would like to thank you for this. This was an excellent topic, and I'm sure that we will going to have, we're going to give you a chance to present what you have applied and some new things that you applied on the main conference in Europe, because this is awesome thing to do, and I'm very glad that we had a chance to listen to this one.
Thank you for having us.
Like, of course, I have sent you the questions. So basically, if you can just record 2-3 minutes by questions, and we'll post that on our LinkedIn profile on Friday as the follow-up of the conference. Once again, thank you, Mate. Right now, we're going to have a short break, and we are going to jump to the final talk for this day. That is going to be delivered by Lucia from Postal Intelligentsia about the data privacy and data privacy manager. So thank you once again, and I'll see you back in 12 minutes.
Thank you.